the idea of this is to get you from potentially knowing basically nothing about PyPy to being able to look into the source and not be completely baffled. I think that's it. So it'll probably take about an hour. We'll see. So, if you get lost or I start blathering about something that's not making any sense or whatever, there's this document called Getting Started, which has this URL, but it's pretty easy to find with Google, or Getting Started will almost certainly get you that URL as the top hit. It talks about where the source lives, how to install Subversion on your platform, and this advice is getting a little bit less relevant now. Subversion's a bit more mature, and sort of ways into the PyPy source. So, this is our big picture of PyPy. PyPy is the implementation of Python written in Python, which is this bit, the standard interpreter, which is a piece of PyPy jargon that gets used quite a bit. So, you can run the standard interpreter is written in Python. You can use CPython to run it, and you end up with an interpreter which is something like 2,000 times slower than CPython to start with. However, we can run tests, which is kind of useful. Yes, and as I said, it's written in RPython, which is our restricted subset of Python, which we can translate. We'll talk about that in a bit. We have our translation tools, which convert the standard interpreter into a compiled, probably C, but maybe LLVM for now, interpreter, which is considerably faster than running it on top of CPython, though not as fast as running it as just CPython yet. These tools are written in using the full power of Python, you could say, which means they're quite confusing. Yes, and of course, producing a fast interpreter which has more features than standard CPython is essentially the point of the whole project. So, looking a bit more closely at the standard interpreter, you can divide it, conceptually speaking, into three main parts. There's the standard object space, which implements objects that look very much like CPython, so integers, floats, lists, dictionaries, Unicode, blah, 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 blah. You know all these things. The parser and compiler, which does what it says on the tin to some extent, and the bytecode evaluator. Now, the bytecode evaluator takes objects, looks at a piece of bytecode which says what to do with those objects, and calls another operation to actually do this. So the bytecode, the point of saying this is that the bytecode evaluator does not make any does not look into the objects at all. It just teaches them as black boxes. We have to add two things, get two things, add them, put the result where it needs to go. Yes, and as the last slide said, all this is written in RPython. It can be translated. So what is RPython? So the first point says it is Python code. This means that we can use unit tests. We can write unit tests that test our standard interpreter, actual unit tests, as opposed to having to compile the whole thing. Well, not quite actually unit tests. The definition of RPython is that after initialization code has run, so after you've imported everything and built some objects, the no more code will run that plays two dynamic tricks. So no reaching into global namespaces from outside and poking things there. No defining functions, so you can make closures. And some of the restrictions are described in the coding guide, which is also linked to on the website. But you shouldn't treat the coding guide as that's not really the definition. That's kind of a guide as to how to write stuff that is IPython. Okay, PyPy is a large enough and complicated enough project that we've invented a fair bit of jargon, which the full-time people will probably use without much thinking. So you should hit us and say, what does that mean? Two very important pieces of jargon are interp level and app level. The way to think about this is that when you're running PyPy on top of CPython, so in the slow interpreter fashion, there is code that is executed by CPython itself. So the bytecode evaluator is at interp level, interpreter level. of course, the code that you type into the interactive interpreter is run by this bytecode evaluator, not CPython's, so we call this application level. It's the application that PyPy is running. And one of the features of the standard interpreter is that it is written in both interp level and app level code. So unlike CPython, where pretty much all of the core stuff is written in C, we have bits which are written in full-powered Python. And you can call from one to the other using this thing called the interpreter gateways, which are, well, fairly confusing. Certainly the implementation is. The advantages of app-level code are, well, it's full Python, so you don't have to worry about these crazy RPython restrictions. It's almost always shorter, less boilerplate. So Holger and Armin gave an example. The find meta class in code is written in app level. The advantage of interp level is it usually ends up being faster to execute. It's lower level, obviously, in some sense. And it can run before much of the system has got going. And also you can avoid sort of circularity issues. If you, like, as Holger again said yesterday, at one point we tried to implement parsing of arguments at app level. Parsing arguments involves calling other functions, which involve passing. We don't do that anymore. The status of the standard interpreter, it's very complete. It's almost, well, it's CPython. I mean, if you fire up the translated PyPy and play with it, it would take you some time to realize that it's not CPython, probably. It doesn't support weak refs. That's about the only major missing feature. So yeah, we pass. I think our definition of core regression test is that we miss extension modules, so we can't run test TCL or something. So if that's not the reason for failing a test, we pass almost everything else. There is still work being done on the standard interpreter, partly because the parser and compiler, there is work being done in work packages 9 and 10, EU jargon, sorry, to allow modification of the syntax at runtime. So you should be able to say, so maybe one day you'll be able to implement, say, some of Python 2.5's features by just fiddling at runtime with the whole setup, which would be quite cool. The standard object space and the bytecode evaluator are really very stable. There's some work has been done on optimizing them, but apart from that, they haven't changed in any fundamental way for several months. Would that be fair? Sorry?
At least half a year.
Right, so yeah. So one potential sprint topic would be experimenting with adding some Python 2.5 features. So there's some new built-ins, or even like things like the extended generators would be kind of interesting. But that's probably quite hard. Haven't really thought about it. So the current focus is more on the translation side of PyPy. It's reasonable to define the translation tools into 4 things. It's not that much of a stretch. The flow object space and the tools that use it analyzes just one code object to work out what the control flow in that function is, rather than doing anything more than that. So we can actually demo this. The Pygame viewer, which is one of our secret weapons. So let's implement the factorial function in an appalling way. So this is where my internet connection is blown up and dot doesn't work on my machine or something. Anyway, this will appear at some point, probably. Here we go. Right, sorry for this delay. So we have, as you can hopefully see here, we have the flow graph of the function. You have one variable on the way in. This is tested using the space operation is true. And depending on whether, if n is true, then there's some operations here which hopefully make some sense. One is subtracted, the function factorial is called. There's a multiplication, and then this variable is returned.
Sorry, just curious, what's the span
I can never remember. Does anyone want to explain? The joke is that you have egg, and span blocks or something.
Yes. It's not relevant. It's because the way the flow object space builds blocks, it's built actually instances of span block and egg block, which are two separate.
Maybe it's better to not distinguish that in the. Everybody wants to know what it is.
I mean,
names for kinds of blocks and branches.
Yeah, yes, so there are names for normal blocks and blocks that comes after the sequence point. So the outputs are constructed. I mean, the flow space is indeed the kind of code that if you work on it, you know what it does for 2 days, and then you kind of forget.
Maybe we shouldn't talk about spam so much with Vikings.
It could be messy. Yeah, so we have this PyGame viewer, which eventually worked. The annotator, by contrast with the flow object space and the flow model tools, takes an entire program, so global analysis, and deduces type annotations, but also some other information. It's to say it's just type inference is slightly missing the point, or simplifying things. It abstractly interprets the flow graphs that are produced by the flow object space to do stuff, and that's enough for now. The R-typer, which is the PyPy's sort of mystery box, does a very important job, which is fairly hard to explain. It takes the annotations produced by the type annotation, by the annotator, and uses this essentially to so the annotator doesn't modify anything in the graphs. The R-typer uses the information the annotator has found to decide how the operations that the program performs will actually be done. So it works out how the types should be laid out in memory, and it translates high-level operations such as get attribute into low-level pointer-ish operations like get field, which just takes a pointer, but takes a field out of a struct. Then we have various backends, which take the low-level operations the R-typer produces and translates it to C, JavaScript, or LLVM. The JavaScript backend can't cope with the full standard interpreter stuff, but it can do simple things, I believe, fairly well. C and LLVM both support everything. Yes, and source generation is one of these things which, by the time you have an R-typed graph which has all these pointerish low-level operations, it ought to be fairly easy to translate this to C, and it's just annoying. So a little bit more about each step in that graph. Right, so there's some babble on the first point here. Control graphs are built by abstractly interpreting the code object using the standard interpreter's bytecode evaluated in abstract domain, the flow object space. And it's quite clever, but as Samueli says, if you need to work on it, you look at it, you understand it, you do your work, then you forget it again. It's stable, it works, we don't really deal with it anymore. The only reason for mentioning it is that the output permeates through the entire rest of the program. So, the flow model. We have this module, pypy.obspace.flow.model, which is, I think, well, almost certainly the most imported module in the PyPy source. It just gets used everywhere. Values are represented in the flow graphs by either instances of the class variable or the class constant, which hopefully is reasonably explanatory. Constants contain a reference to the actual Python object that was present in the model. Variables are things which are, well, not constants. A function's control flow graph is represented by an instance of this class function graph, which is made up of blocks and links in the kind of obvious way. If you look at the Pygame viewer, which system preferences has dumped core, good. This is a block, this is a link, this is another block. More links, this is a special kind of block that is where things are returned from. Each block contains a list of space operations, which is what the next slide's about. Space operations have a name, so add, mul, simple call, whatever, get attribute, get item, lots. The graph, a result variable, so where the space operation will put its result when it's executed, and a list of arguments, which are constants or variables. The graph is naturally produced in static single information form, which is a even more restrictive form of static single assignment form, if you know what that is. Each variable is only assigned to in one place in the graph. The restriction that distinguishes static single information from static single assignment is, roughly speaking, that each variable only ever occurs in one block, and if it's used in another block where control flow travels, then the variable is renamed as it passes across the block. It's just, I think the question is, why do we produce it in static single assignment form?
Why do we need to rename the variables?
Well, not really. Is there any? It makes analysis easier because you can always tell.
You always know that the variables never leave the block.
You can always find all the places that a given variable is used very easily because you only have to look at the block that defines it. And it's easy to see if it will be propagated out of the block because there'll be a renamer. What's the block?
A lot of things get more explicit.
Make it easy to
Yeah. I mean, and also it's just, part of it is that it's just the way it turns up in the way the model is built makes it happen naturally. So unlike standard compiler books which talk for pages and pages about how to use dominators to compute SSA form, it just lands in our lap. Which makes reading compiler literature rather strange. So, yes, some examples of space operations. This Python code, you would hope, gets translated to the space operation of the name of getAttr, which has two arguments. The variable representing the object, which attribute you're getting, a constant string, y, and then a variable representing the result. And, well, you can read the others. I mean, it's never going to be obvious from just this tiny piece of code whether you get a variable or a constant, so I've decided arbitrarily. So, the annotator. I mean, type annotation is fairly familiar. It's done in many different contexts, explicitly and implicitly. I mean, ML and Haskell all use type inference. Common list of implementations tend to do a degree of it. It associates information about which variables with information about which values they might contain. I mean, an instance of this information is type, though also we store other information. So there's an annotation for whether an integer can be proved to be non-negative or not, for example. The way PyPy's annotation works is you build up a system of objects. So you import modules, you define functions, and then you give it an entry point and say, I need to annotate this actual function. This means that initialization code is never seen by the annotator. So we have code that uses exec to define a bunch of similar functions, or you can define closures and store these closures in the global environment and call them from your code. This is what I was saying about our Python is defined as being static after a certain point. It also means that some annotations actually contain references to objects, as opposed to just being static data in some sense. The annotator works by abstractly interpreting, which is something we talk about a lot in PyPy, the control flow graphs. So annotation starts, you give annotation an entry point, you say, I'd like you to annotate this function, assuming it is called with an integer, say, and then it will proceed recursively through the graph, building flow graphs of functions that function calls. So annotation and building of flow graphs are intermingled. There's this paper on the website called Compiling Dynamic Language Implementations, which describes in quite some detail how the annotator works. Well, as opposed to working on source code, say, like an ML type inference engine would. Sorry, the question was, what does this bullet mean? What does working on live objects mean, and why do I consider that to be unusual? Sorry? Not really. I don't. So no, you import the code, and then it's all in one Python process. Yes, essentially. So the code, the annotation, and the code that's being annotated live in the same process. So whether you actually run the code that you're annotating is not run in any real sense. Well, sort of it is, but that's a cheat. I'm trying not to mention that. Worry about that for now. Yes, something like that. So the annotator is well documented. There's this paper on the website which is mostly written by Armin, but with bits by me and Samuel. It considers a block at a time, and it maintains a list, or pile, because I didn't want to. It's not ordered in the sense that you might assume from a list of blocks that will need analysis. So when you get to a branch, it queues up both blocks for later analysis, and then it'll pick one and then. Some blocks will get annotated more than once because at first, because the annotator may believe that a block, say a variable, can only ever be the constant 1, but then may have to redo it when it realizes that it can actually be any integer at all. Yes, and this is, as a sort of classic for things like this, it uses a fixed point approach. While there are blocks that need to be annotated, annotate a block, repeats. So what does the annotator produce? It doesn't. The annotator merely sort of observes the graphs. It doesn't change anything. And the end result is essentially this enormous dictionary which maps instances of variable to a subclass of some object. So there are subclasses, some integer, which hopefully is, which is not quite as simple as it might be because it contains information like whether we can prove that the integer is non-negative and how big the integer is. Some list, which maintains information about what the type of the elements of the list are. Some instance, which is an instance of a user-defined class, and some PBC, which stands for some pre-built constant, which is kind of a bad name because they're not necessarily constants, are they? No. No, hang on, they are actually. Yes, they are, because things that aren't constant get treated as some instance. Though we've gone back and forth on this a few times, which is why it's confusing. And the most important examples of things which get annotated as some pre-built constant are functions and classes. So this is one of the things I was saying, that it's not just type annotation. If you're calling a function, if the source code says x equals f of t, you better have some idea what values t takes, f takes rather.
So if you have a variable that crosses blocks,
Mm-hmm.
does it get 2 entries in the dictionary?
What do you mean by a variable?
When you talk about a variable being more than one block, you get it. But
Yeah, but then there's a new variable in the next block. So essentially, yes, the logical variable will have 2 entries because there are 2 actual instances of the class variable associated with it. Oh yes, R-typer. We've never really come up with a good name for R-typer. It could be called a specializer, but that has another meaning in the PyPy jargon. So rather than using the same word for twice, it just seems better, at least to me, to have a more or less meaningless name that we can attach meaning to. The R in R-typer could stand for RPython, but it could also stand for representation, because a lot of what the R-typer does is it decides how high-level types in the input program are laid out in memory and treated. So the R-typer has some support for laying out objects in a C-like model with pointers and structs and arrays and atomic data types, and also it has support for representing things as instances of classes in an OO-like language such as Java or Smalltalk, though this is mostly theoretical at the moment. There is some code, but it doesn't actually, it's not complete. Originally we tried to do the job. One of the things about the R-typer is that we didn't know we needed it. So for example, there was no mention of it in the description of work that we submitted to the EU 2 or 3 years ago, because we just had no idea that we were going to need it. And the need emerged when we tried to write source generation. It's kind of easy to do source generation for, say, a function that manipulates integers, because, well, integers aren't that complicated. There aren't that many ways you can represent an integer. When it comes to things like classes and allocating memory and handling pointers, it just turns out that trying to decide how structures are laid out at the same time as generating the source just does not work. That's one of the reasons I think the R-typer is interesting, is that it's not part of the standard compiler toolset. If you go and read the Dragon book, you won't find anything that's even remotely like the R-typer described in it. So unlike parsing or even type inference. So talking about the reason representation selection is an issue is that we don't always have to represent things which are the same type in the source program the same way in the translated program. So for example, we treat the return value of range in a special way. We know that a lot of the time, all that's ever going to be done with an instance of range is to iterate over it in a for loop. So the annotator can tell whether whether the return value of range is ever going to be mutated. And if it's not, well, we can just represent it as actually it's just 2 integers, I think. Well, no, 3. The current value, the step, and when you should stop, as opposed to actually allocating a list in memory or anything like that. On the other hand, but this means that code that small fraction of code that takes the return value of range and then reverses it or inserts new items in the list doesn't break in any way. It just works. And that call to range will return a normal list. So the representations that we choose for objects are described in terms of types, which are defined in this module, pypy.rpython.lltypesystem.lltype. LLtype stands for low-level type, occasionally referred to as L2, because there is L3 as well later on. So these classes describe a C-like memory model, so as I said earlier, arrays, pointers, structs, floats, signs, which are integers. The difference between GC struct and struct is that GC struct is assumed to live on the heap, whereas a struct is something that's embedded in a larger structure. So you can have a GC array of structs, but not a GC array of GC structs, because GC structs would be expected to live on the heap, not as part of an array. The convention is that variables holding instances of LL type are written in all capitals, so this capital type is quite a common thing you might see in the PyPy source. This isn't entirely consistent, of course. That would be too easy. Another remarkable, slightly surprising thing about this LL types is that you can actually write code that says lltype.malloc, an instance of type, and you get back something that looks somewhat like it will at C times. It does checks that you don't assign floats to signs and whatever. This is a result of Samueli not being able to sleep very well one night, I think. So, in some sense, you could say the main job the R-typer does is it attaches this attribute concrete type to all the variables and constants that occur in the input program, the graphs of the input program. This concrete type is an LL type, so for something that's annotated as some integer, it will probably be lltype.signed, but not always. However, while R-typing is going on, there's these classes called repr, which I guess stands for representation, which are associated with each annotation, so not quite associated with the variable, they're associated with the sum PBC or the sum integer, which know how, essentially their job is to translate the high-level operations like add into the low-level operations like integer add. Which is what I just said. Yes, the high-level operation add applies to strings, floats, integers, probably not much else. And if we just left... Intermission? Well, if I was waving my arms particularly hard when it came off, it would make more sense. Okay, so if we just left the high-level operation add in the graph and then tried to generate the source, the code that generated the source would have to check whether, well, add's a bad example because it probably wouldn't really, but anyway, it would in principle have to check that each time you generate, you can see this operation, which types you're adding. And this doesn't really work. This is one of the reasons the R-typer was found to be necessary. And it's better to have monomorphic, in the sense of not polymorphic operations, int add, float add, string add, except, well, there isn't string add, but I'm not going to explain why not either just yet. Yeah, and some operations are much more complicated than the mere adding of two integers. If you, what looks like, when you instantiate a class, you just call the class, right? It's Python. This is transformed into quite a number of low-level operations. You have to allocate some memory, you have to assign the type pointer, you have to set up the object to be an instance of the class. So the way this works is, for each operation, we find or create an instance of repr for each argument, or each argument's annotation, pedantically speaking. These are asked, in a sense, which I'm not really going to explain, which low-level operations the high-level operation should be replaced with. So an example, we start with this space operation, which is very like something that was seen earlier. It's the addition of two variables, and the annotator has worked out that these variables are going to be some integers. So we call this method on the R-typer. There's a class called rPython typer, I think, though instances are canonically called R-typer. We call getRepr or getRepresentation for both variables, and we get an instance of integer repr. We end up, and then through some various steps, what eventually happens is this method rtype add. So the add, this bit of the method name comes from the name of the space operation. Is called on this thing called a pair type. Not going to explain that. Which knows that when you add two integers, you should make an integer addition operation, which replaces the space operation in the graph.
On the middle bullet, when you say same for by, that doesn't mean it's the same instance of the integer.
In fact, it is, but in principle, it doesn't matter. It won't necessarily be. Yeah, but again, because integers are simple things, essentially. There's no internal state. Do you want to quibble?
All by the trap really takes an annotation.
Not a variable?
No, there's a thing called binding wrap.
I see. Okay. I thought get repro was magic and took both, but no. Okay. Well, things like input const, which takes both a repro and a lower. Yeah, okay, so this should say binding repro. Though, in principle, you won't actually be doing that. This code is written, so you probably won't be looking at it. Source generation. The approximately maintained backends are C, which I hope you're all at least aware of, JavaScript, which is mainly maintained by Eric Ranvier at PAP, and essentially it's an open source project and we can't stop him. Which is perhaps a bit harsh, and LLVM, which is a low-level virtual machine. It's an open source portable assembler, roughly speaking, with quite a good optimizer. All the newer versions of source generation work in two ways. We go through every graph and work out what each variable is going to be called, essentially, and what type in the low-level language it will have. Then we just go through each graph in turn and translate and make the operations. So for integer, when you have an integer add in C, your variable is called V1 and V2. You just write V1 plus V2. It's not hard. Actually, it's just annoying. This bit is the more annoying part, probably. I mean, this bit is also fairly annoying for one of the things I haven't talked about at all, which is exceptions. Yes, so we've basically come to the end of my introduction, but I hope I've told you a reasonable amount, but these are just some of the things that I haven't mentioned, so hopefully when you come into them, it won't be a complete surprise, though you'll have to ask someone what they actually are. Specialization of functions. You would think, naively, that one function in the PyPy source, in the source of the input program, would translate to one function in the generated source. This isn't true, it turns out. You can both have no function in the input source and still want to be able to call it. This is for like external functions, for example, os.open. Or you can have one function in the input program and want to generate several different versions of it. So there are functions which are called with many different types, which isn't the way our Python works, but you can make it work in special cases. And you end up with an f_int, f_string, if you called it with an int and a string. External functions, again, it's a bit messy, but you can define a function which is not defined by PyPy itself, by Python code. Low-level helpers are used in the R-typer. They're sort of annotated in a special way and they work a bit like C++ templates, but without the angle brackets. Garbage collection policies. One of the current pieces of work is to be able to decide whether you're going to use ref counting or the Bohm GC or some mark and sweep code that we have written or a semi-space copy and collector. And we want to be able to choose with these without impacting the input source to the standard interpreter. The JIT, which I don't really understand what's going on there at the moment. Constraint solving and logic programming and integration. There's work being done about integrating somewhat Prolog style programming into Python. I don't know much about this either. Geninterp is a speed hack, I think, roughly speaking. Pair types are essentially a cute hack way of implementing multi-methods, and they're used by the R-typer. Back-end optimizations. Between R-typing and source generation, you can optionally run what would get called back-end optimizations in the PyPy jargon. So this includes such things as inlining functions, converting mallocs which don't, I don't know, if something is allocated on the heap and it's never doesn't escape from the function, you can not bother actually allocating it. All sorts of things which I can't remember. Exceptions in the flow model, I didn't these neat flow graphs you get become more complicated when you have exceptions. I didn't want to explain the details. Multi-methods in the standard object space. There's a different implementation of multi-methods in the standard object space, but as the standard object space mostly works these days, there's not any pressing need to explain it. So a little bit, this is more, not so much about the hardcore of how the PyPy is written, but how the code is written, more about how it is actually written as a process. Only one more slide, so you don't need to stick it back on that firmly. So there's this coding guide, which I referenced. So it talks a bit about RPython, but it also talks about style issues. So it's PEP 8 from the way Python is supposed to be written in the standard library. 4 space indents, no tabs in source, lines wrapped at 80 columns, that kind of thing. We use test-driven development. This is actually extremely important in some areas because it's very easy to write tests that don't actually test anything because something gets constant folded away or other obscure things happen. So if you're trying to fix a bug, it's a really, really good idea to make sure you have a test which fails first. Otherwise, you're not fixing what you think you're fixing. When we're not sprinting, we mostly talk in the PyPy channel on Freenode. It's a fairly busy channel. It's quite variable, but there's usually people there and people active, especially, though mostly it's us Europeans, so you can predict which hours that's going to be. We have PyPy sync meetings at 1 p.m. European Central Time, which works out at something like 4 a.m. in the morning here, every Thursday. So that's when we get together. I mean, if as a result of this sprint you're also energized that you all want to participate, presumably we'll move the meetings to a time that's a bit more US friendly. Oh, this is an unfinished slide. Development process. Well, we use PyTest a lot. PyTest has various features which are useful in general, but also some specific PyPy features, like if you pass this -- view to PyTest, you'll usually, depending on how the test is written, get to see the flow graphs at various stages as the test runs, and we use the PDB feature of PyTest a lot. So when a test fails, you drop into PDB and things like that. And I think that is it. So I hope that helps.